Okay, I'm not going to do the introduction anymore. So we're talking about the theory of computation. So this is basically it. There are a couple different approaches for the theory of computation. Either we do mu recursive functions, or we do Turing machines, or we do lambda calculus. We're not going to discuss lambda calculus, but we are going to discuss Turing machines and mu recursive function, and we are going to prove that they are the same. But then the fact that Turing machines and mu recursive functions, the fact that they capture our intuitive understanding of computability, is known as Church's thesis. There is no way to prove it because there is no framework to prove it. We do not have the definition of our intuitive sense of computability. But whatever this is, the fact that it is captured by these two definitions mentioned is called the Church thesis. But before we start, we have to discuss what it means to have a countable set. And so I'm going to give a very short description that goes like this. So if you have a finite set of, like, I don't know, three things: a guy or a boy, a square, and a triangle, right? And let's say I want to ask you to, so let's add the fourth thing. Triangle and, I don't know, a rose. So this is a rose or whatever, right? So now let's say I want to ask you to count how many things are there. What you really are doing is you go 1, 2, 3, 4. So what you're basically doing, that you have something in your head called 1, 2, 3, and 4. Let's call this guy bold 4. So a finite set of 4 elements, something that you have in your head, that you learned it in school. And what you're doing is you're basically creating a bijection. 1 goes here, 2 goes here, 3 goes here, and 4 goes here. So what you did is you had this guy 4 in your head, and you created a bijection, let's call this guy F, into our set, let's call this guy S. So this is all you did. So, and in your first grade, you learn not to miscount things. Like, for example, when you're in the first grade, you know that you are not supposed to do this. You're not supposed to go 1, 2, well, this is actually factual. Let's go like 1, 2, 3, 4. You're not supposed to do this, right? Because then the function that I just drew is not injective anymore. And what you might conclude if you do this, you might conclude that this set here, only this is 4 elements, because there is a function from 4 into this guy, but you counted this boy twice. Right? So this you're banning. You're not supposed to do this. Another thing that you're not supposed to do is to count like this. So let's say you have the 5th element here, namely circle. And let's say you're counting again, and maybe you're doing something like this. 1, 2, 3, 4, and then you said you're finished. You're also not supposed to do this because you're missing an element. So your function has to count all the elements, and it has to count everything once. These are the 2 requirements of what we call injective and surjective function. So that means if you have an injective and surjective function from a finite set, then you know that, as you said, the cardinalities are equal somehow, and they are the same size. The same exact intuition now goes, so I have this set natural numbers with 0, and set A, I will say that they have the same cardinality if there exists a bijection. That's it. This is all there is. You're doing the same exact thing as you were doing from finite sets when you were counting. Now you're counting from the natural numbers. And so the word countable tells you that this set can be counted. So I will say a set is countable if there is a bijection from natural numbers, or the set is finite, meaning there is a bijection from finite sets. That's all there is. So this is the definition of countability. And maybe let's go back here. And we did this, but we just lost the recording. So we have the definition of countable, and we just saw that 3 times n, 0, which is a set of 0, 3, 6, 9, 12, 15, 18, and so on. This set is also countable. And how is it countable? Is that really I can count it. 1, 2, 3, 4, 5, 6, 7. So what I'm really doing I'm doing this like this. So I'm creating a bijection from this guy. So basically I want to create a bijection from 0, I forgot. So I always include like this. So the zeroth element will be my first element instead of the first element. Okay, so this thing is countable. But there are some other things that are not so obviously countable. For example, the set of... is this countable? So set of whole numbers, so negative numbers and positive numbers, is it countable? So what is the bijection? So I can just go like this. This is 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, and so on and so forth. I go just back and forth. I do not care about the formula, but you see that every number is only counted once and every number will be counted. Right? So this is also countable, and so on and so forth. Let's go back to our slides now and slow down because we're back to where we were. So example here of a countable set will be even numbers. Of course, we did multiples of 3, but even numbers are also countable. And now the first thing is, so let me get back here. So another example of countability is, let's say A is my alphabet. Some alphabet. So A is a finite set. This is what it means that this is alphabet. What I'm claiming is that A star is countable. Can you see why? For example, if I take B, 0, 1, I'm claiming that B star is countable. So what does B star contain? So B star contains an empty string. It contains 0, it contains 1, it contains 0, 0, 0, 1, 1, 0, 1, 1, then 0, 0, 0, and so on. Okay, I just wrote it out, showing that this is countable somehow. Can you tell me how should I count the B star, the strings?
Since there are no multiple same objects in the set, we could just say that epsilon is 0, 0 is 1, 1 is 2, 0 is
1. But is there any way to arrange them? This is what I'm talking about. Can you, if I do this, can you tell me what is the 76th element here? So the question is it possible to do for any finite set? I wrote it down in some sense here to give you a hint how should you do this.
Yeah, we can, in a sense. Depends on, well, if we did the B star in general and kind of...
So exactly as you said, you can do it for any A. So you look, let's say AI will be strings. So strings of A of length I. So for example, A0 will be just epsilon. A1 will be just elements of A. So it will contain A1, A2, A3. So let's do in our case. So B0 will be just an empty guy. B1 will be just 0 and 1. B2 will be 0, 0, 0, 1, 1, 0, 1, 1, and so on, right? B3 will be length 3 strings, and you can order each one of them lexicographically. That is the keyword that I was looking for. So you can order them that first you put 0 here, because you know that 0 is less than 1 somehow. You can choose to put 0 first, then first you look like in your dictionary. First you look at how are the words ordered, right? You have an ordering on your words, like your letters, A, B, C, D, E, F, G, and how are they ordered in your vocabulary or in your book? Is they ordered lexicographically. First you look at the first letter, if it coincides then you look at the second letter, and so on. You do the same exact thing here. ხო, მაგრამ ეს მარტივია რა.
strictly infinity sequence-ი გვაქვს რაღაცა და set of 11
So, but does everybody agree that you can do this? For if you have a finite set A, what you do is A is finite, right? That means you can number the letters in A, going A0, A1, whatever numbering you choose. And then lexicographically, you will assume that A0 counts before A1, so any string can be ordered. For any string, you should be able to tell me this string is less than the other string. So it comes before, so you order them lexicographically. This is what the proof says here, basically. So again, so this means that if you're able to put it in the list, then it means that it's countable. Like for example, I just give you a food for thought. Can you write real numbers as a list like this? Right? You might think, can I write real numbers? Maybe you can, maybe you can't. We'll see it in a minute. So okay, this thing is countable. The next thing that we're gonna see is that pairs are also countable. Can you see why? So what we're claiming here is now I take this function, n0 times n0. Why is it countable? So these are all pairs, right? So these are pairs A, B, such that A and B are both natural numbers. So what we can do, so let me show you denote by SI those pairs that sum up to I. For example, this says that S0 will just contain one pair, 0, 0. S1 will contain two pairs, 1, 0 and 0, 1. S2, how many pairs will this contain? All that sum up to 1, so this will be 1, 1, 2, 0, 0, 2, right? So you can do this, S0, S1, then do S3, and so on. Continue doing this. And now each SI now, similar to our alphabet, can be ordered lexicographically, meaning that this comes before this guy, because it starts with 0. Same way you can order these guys lexicographically by comparing the first, which one comes first? I compare the first letter, right? So 1, 1 comes first, then 2, 0, 0, 2 comes first, then 1, 1, and then 2, 0. So the same way you order in your vocabulary, you can order each SI, and then group them together exactly like this, and you will get this here. That 0, 0 comes first, then 0, 1, 1, 0, then 0, 2, 1, 1, 2, 0. So this is S0, this guy is S1, this guy is S2, and so on. And you just put them together the same exact way as. But let's just continue with this, and we'll see. For now, what we see is that natural numbers is of course countable by definition. It's a bijection. Natural numbers is in a bijections with itself. Then A star is countable for any finite A, and we saw that pairs are countable. The next thing we see basically is that you can generalize this and say that if A and B are countable, then A times B is always countable. And this holds for all finite K, which is an exercise, meaning that triples are also countable, quadruples are also countable, and for any finite K, n to the power K is countable. So if your set is countable, that set to the any multiplied by itself as many times as you like, but finite many times is countable. So far we only see countable numbers. So now let's look at a very important example of an uncountable number, which actually is the same as, so let's try to copy this. So let's, how much time do I have no watch? So when the time's up, you tell me because I left my phone. Romelia? Takucha. Okay, so let's look at uncountability, right? So what is uncountable? So I'm gonna give you the same thing in 3 different ways. And let's at least do this. So first, let's look at natural numbers. Again, let's say with 0, as we like 0 so much. We look at natural numbers, and I'm looking at all possible subsets of natural numbers. So I'm looking at the set. So 2 to the power n0. Hopefully it turns, yeah. So I'm looking at this subset. What is this? This is all possible subsets of natural numbers. So what does this include? It includes empty set. It includes, let's say, 2 and 4. This is a subset of natural numbers. It includes 6, 7, and 0. It includes this guy as well. It includes all even numbers. So 2, 4, 6, 8, and so on. Right? You see that all possible subsets I can take from natural numbers can be finite or infinite. It includes natural numbers itself, and so on. So there's many of them, right? So does everybody agree that this is something, right? So, okay, now the second thing I'm claiming is all binary strings, but not B star, rather all infinite. So I'm looking at all infinite binary strings. B star only contains finite binary strings. And first, I'm going to tell you that these 2 things are the same. There's a bijection between these 2 things. Why? Let's say I give you a subset of, so let me construct an infinite string from a subset, let's say. So if I give you a subset of natural numbers, let's say this guy. So I give you a subset. So let's first write down natural numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. So this is natural numbers, right? So giving a subset of natural numbers, it amounts to choosing some of these numbers, right? So for example, giving you an all even numbers amounts to choosing these numbers here. Do you agree? Do you agree that any subset of natural numbers is basically a choice? But however, any choice can be seen as a binary string, meaning I chose this, I didn't choose this, chose this, didn't choose this, chose this, not this, not this, not, and so on. So now what I'm claiming that every infinite binary string represents a subset in natural numbers. Okay, so if this makes sense that every infinite binary string represents a subset of a natural numbers, then tell me what is the binary string that represents this guy? Empty. All zeros, exactly. What is the guy that represents this thing? All ones, right? So this guy, for example, is represented by 0, 0, 1, 0, 1, and then all zeros. You see, because the second guy, so 0, 1, 2 is chosen, and 3, 4 is chosen. So basically, all subsets of natural numbers and all infinite binary strings are the same thing. Now I'm going to give you a third characterization, which is actually used here, by the way. Yeah. So all possible functions, so this is a set of all functions such that function goes from n0 to b. So what is this function, basically? This function, what this function is, you have natural numbers, 3, 4, 5, 6, 7, 8, 9, and so on. So you have natural numbers, and this function maps to 0 or 1. So you basically have this goes to 0, this goes to 0, this goes to, maybe this goes to 1, this goes to 0. So you have this, you see that this is basically an infinite string. So it's it is an infinite string, but it can also be seen as choosing this subset. So it's subset 3, 6, 8. It's also an infinite string that corresponds to this thing here, but it's also a function from natural numbers into 0, 1. So now you should agree that all possible functions from natural numbers into 0 and 1, so Boolean functions, also all possible substrings of natural numbers, and all binary infinite strings, they are all the same. And now the claim is that let's choose more computer sciencey thing, that all infinite binary strings, this set is uncountable. And the argument I'm going to use to prove this is called Cantor's diagonal argument, and this is yet another argument. So we use induction or Cantor's diagonal always. So how does the proof go? So now I'm looking at the second picture, right? So I'm proving that three things simultaneously. I'm proving that all functions from natural numbers to binaries are uncountable, all infinite binary strings are uncountable, and all subsets of natural numbers, set of all subsets of natural numbers is uncountable. So how do I prove this? There's many ways to do it, but the most famous one is assume it's countable. You don't have to do this, but let's say there is a bijection, let's call it F. Let's call this guy B tilde. It emphasizes this is not B star, this is B tilde. This is infinite, this is much bigger. So let's say there is a bijection from natural numbers to B tilde. Right? Let's say this thing exists. Then what I can do, if this exists, I can write F0. This is some string, right? This is some infinite string. So let's say 0, 1, 0, 1, 1, 0, 1, 1, 0, and it continues infinitely. Then I can write F1, which is 0, 1, 0, 1, 1, 0, 1, 0, 1. So it differs somewhere. Then I have F2, which is 1, 0, 1, 0, 0, 0, 1, whatever. So I have this string that this continues infinitely. So if I assume that there is a bijection, or bijection, then I can write down the infinite strings like this. And now what I'm going to do, I'm going to write you a string here which is not in here. How? First I'm going to look at the first element of F0. The first element of F0 is 0, so I will write the opposite. I will write 1. Then I'm going to look at the second element of F1. This is 1, so I'm going to write the opposite and I go 0. Then I'm going to look at the third element here, and it's 1, so I'm going to write an opposite and I go 0. And I continue doing this, meaning I'm continue doing this like this, going down on the diagonal. That's why it's called the Cantor's diagonal argument. And let's say these are some numbers, I don't know, 1, 0, 0, 1, 1, 0. Then I'm producing the opposite. So 1, 0, 1, 0, 0, 1, and so on. So what I'm claiming now is that this guy here is not on this list. How is it not on this list? How can I claim that it's not on the list? Why? Because it's not the first element. Why? Because it differs in the first spot. It's not the second element. It differs in the second spot. It's not the third element. It differs in the third spot. So this means that there is an infinite string such that your function never hits. So it's not surjective. So it cannot be a bijection. So assuming there is a list, assuming there is a bijection, I constructed a string which is different from any string here, so it's not bijection, so I arrive at a contradiction, so the bijection does not exist. Here is the same argument here, but formally written out. Exactly, you can write it out this way. So imagine these are my infinite strings now, and what you're really constructing is a function that adds 1 with O plus operation. So what I was doing basically here is Raiho. So what is this? This is F0 at 0, meaning F0 at 0 somehow means this function's first place, the zeroth place of this function, XOR 1. This is what I was doing. So I was changing, this was my new functions G at 0. So G at 0, if I call this guy G at 0, meaning that G in the first place is whatever F0 was at the zeroth place plus 1. G at 1 will be whatever F1 was at first place plus 1. So this is what is written basically here. Oops. So this is what is written here, that G at x is f of x at x plus 1. So G at place 5 is you find a function, the fifth function, compute it at the fifth place, the fifth string at fifth place, and add 1. And you will see that G is not on this list. Because if G is on this list, it has a number fx, and fxx is gx, and fxx plus 1, you arrive at a contradiction. Basically, an uncountable set exists. And you can do the same exact argument with real numbers. You can write down all the possible real numbers and then go by the diagonal and create a new real number which is not on the list. This is what Cantor did, basically. But this also works for infinite binary strings. So all possible infinite binary strings are not countable. And now we move to actual definition of primitive recursive function, but I guess my time is up, right? It's okay. If we have 4 more minutes, actually, let's ask questions about this. So is the... So let's pause this. Let's stop.